In this video, we're going to introduce through example the process of implicit differentiation. We're going to look at the circle x squared plus y squared equals 16, which is a circle with radius 4. Again, the 16 is the radius squared, 4 squared. So we have this circle defined, and what we're going to do is start with that formula. The thing we know is that every point on this circle is satisfied or satisfies x squared plus y squared equals 16. No matter where we go, that's the case. What we're then going to do is use the Leibniz notation here, and we're going to transform both sides of our equation. If these things are always equal, even though x and y are changing, they always add up to 16, which is a constant, then that means that the rate of change should be equal as well. When we take the rate of change as we change x, the left-hand side and the right-hand side should also have the same rates of change. The right-hand side in this case is dead easy. The derivative of any constant is always 0. We've also seen parts of the left-hand side. If we ask what the x derivative of x squared is, well, we know that. It's 2x. So this part here becomes the 2x. The question is, what do we do with the x derivative of y? And this is why, especially for implicit differentiation, it's really helpful to use the Leibniz notation, this fraction d dx, which is the verb take the derivative of something with respect to the variable x specifically, because it's going to help us separate how we do this derivative here. And I'm just going to do a little side note. If we take the derivative of x squared, let me be clear about how this works. We actually get the 2x, and then remember there is a chain rule which would take the derivative of the inside function, which is dx dx. Well, what we've been saying all along is that derivative is just 1, so we essentially can ignore it. When we do the same thing with y, though, it's going to be a little different. To highlight the difference here, if we had the derivative of y squared with respect to x, what we think of is y is a function of x. If we pick a point here, at least locally, we can determine that y is a function of x. We can't do it everywhere, but we can do it on a point-by-point basis. And if that's the case, then the chain rule says anything squared, the derivative is 2 times the same thing. And then we're going to follow up in exactly the same way we did before. We're not playing favorites here. We're not doing special things for different functions. However, in this case, the variable that we're dealing with is y, and so we get dy dx, because the x derivative is what we're taking. Here we got dx dx, and that went away. But here the dy dx is actually a new term. This is the slopes on the curve. And that's exactly what we would have said was the derivative of a regular function. Here it just happens to be blended with some y values. Let's see how that plays out over here. The derivative of the x squared is 2x, and again I'm going to put the dx dx here in explicitly, and we'll simplify it out in a moment. Then we get plus the 2y dy dx. And if you can see why we have these two slightly different terms, then you understand everything you need to know about the technical side of implicit differentiation. Both derivatives are with respect to x, so both the denominators are dx's, but the variable that we used is different in these two expressions because one started with x's, one started with y's. Now we can simplify. The rate of change of x with respect to x is just 1, and there's just nothing we do to the right-hand side or the right-hand term here. It just stays as dy dx. And in fact, going back to our question, find a formula for the slopes. Well, that is exactly what we mean by dy dx. So now we just solve for that expression in our equation. We'll see how this plays out. It can take some convincing to believe this, but we'll see how effective it is through several examples. So we have 2y dy dx is equal to, we'll bring the 2x over, it becomes negative, and then we bring the 2y over as well. We get negative 2x on top, we divide through by the two y's, and we end up with negative x over y when we tidy that up. And so our formula for slopes is negative x over y. On that specific circle. Let's follow that up with some calculations for a specific point and see if it actually is working the way we expect. Here's that same circle again, and we're going to pick the point to root 12. So we had the derivative dy dx was equal to negative x over y. At the point to root 12, we're going to have dy dx equals the x value on top, but negative over root 12. And putting that into our calculator gives us a value of around negative 0.578. Or 0.6 is probably as close as we're going to get graphically. Let's confirm that. If we have a slope of around negative 0.6, then every one step we go to the right, we should go down by negative 0.6. We go down by 0.6. So over here, we go down by 0.6, we're about here. And we go down by 0.6 again, we're about, hey, this is looking pretty good. Let's draw that out there. A little more accurate. And do the same thing on the other side. We go up by 0.6, up by 0.6, and that seems to match the graph quite nicely. Excellent. So the idea inspired in the last page by taking the equation, it's not a function, that's fine, but as long as we do mathematical operations equally to both sides of this equation, we're fine. And all we chose to do here was do a new operation, which is take the derivative with respect to x of both sides. And it got us to a result that was our usual dy dx in the end, being computable by plugging in some values. Once we compute those values at a point, we get slopes that make sense with the sketch that we're looking at. So this is fantastic. Now, is there something different about what we just found? Well, if you think of what we've seen before versus what we just saw now, if we had earlier, we had y equals things like x squared, that gave us dy dx, it was just 2x. And if we had y equals e to the negative x, that gave us the derivative of negative e to the negative x. And what we see, if you keep repeating this over and over again, is that these only had x's in them, which made sense because you were differentiating the right-hand side, and if you like, the left-hand side was just y, and its x derivative was just dy dx. But the right-hand side always was only x's in a function. That's a little different here because we have x and y in our slope formula. Not a problem, but just something new. And it makes sense that we would need that, of course, because if we think back to our circle, it wouldn't be enough to say, what's the slope at x equals 2, because there's actually 2 points on that circle where x equals 2. So we'd have to be able to distinguish the slope at this point from the slope at this point here. And that we can do by knowing both the x and the y value of the point on our circle for this example, or point on any relationship going forward. And that lets us uniquely identify the slope at a single point when we know both x and y. So that's our first example of working with implicit derivatives. And again, the fundamental operation is start with an equation and then simply differentiate both sides with respect to a single variable. We're going to see this applied through several other examples to give you some practice.